Redo the video now. We're going to calculate the maximum power transfer. What does ZL should be to give me maximum power transfer? This is my load here. That's why we call it ZL, or stands for load. So this is my load, and I want to know what value for Z I should put for the load to get a maximum power transfer. Yep, I mentioned that a while ago. I said the conjugate of Z theorem. Maybe we'll go through the math and derive it. So if you try to calculate what the current through this first, you know you can combine these two impedances together. So you get I equals Ohm's law, V divided by Z. And V is what? V Thevenin. And Z will be Z Thevenin plus Z load. Now let's think about this. I'm assuming Z Thevenin here is going to be real portion and imaginary portion. So let's call it ZT for ZT. I said T and I wrote L. I'm not going to write Thevenin, so I go ZT plus an imaginary value of, R, real portion and imaginary. I should use different, instead of Z Thevenin, well, I'll leave it Z Thevenin. It's going to have a resistor portion, a real portion, an imaginary portion. So let's call it, it's going to be R T plus some imaginary value, and we'll call the imaginary value, I don't know, X. A real portion plus imaginary. And the load is going to have what? Some R load plus some imaginary value, X load. So if I plug them in, this will be what? V Thevenin over, I can combine the real portion together and the imaginary portion together. Now, what is the voltage across the load? V load. Well, we know ZL times I. We do the math. That's V Thevenin times I. Well, I'm going to multiply by ZL there too. So this is I, which is V Thevenin over R Thevenin plus RL plus J X Thevenin plus XL. Then you multiply by ZL, which is what? RL plus JXL. I want to find what the power now. Power equals what? Voltage times current? Maximum power transfer. You go to power, which is I times V. You multiply this by that. Well, the only difference is going to be what? This value. So it's going to be V Thevenin squared times RL plus JXL over this one squared. Sometimes I say, why am I getting myself into this math? Just put the equation there. Now, what is the magnitude of that power? What is the magnitude? I probably would have done it easier if I did the magnitude of each one first before I did that. The magnitude of the power Remember, when you have complex number, you take the real portion and you square it. Take the imaginary portion, you square it. So V Thevenin squared times, let's take the value of that, that will be the square root of r sub l squared plus x sub l squared. Over, yeah, well, the j disappeared. You take the real portion, the imaginary portion, then you take the square root of that. You know, over, this one will be what? The magnitude of r is r Thevenin plus rl squared plus x Thevenin plus xl squared. And you really want to take the derivative of that and set it equal to 0. I'm not going to go through the math, but let's think about this. Just mathematically, we can take the derivative, set it equal to 0. You have a fraction. For the fraction to have the largest value possible, you need the bottom to be what? The smallest value possible. I mean, we can take the derivative, set it equal to 0, and go through the math. I'm going to bypass that. I'm just going to use logic here. You have a fraction. For this fraction to have a bigger answer, you need the bottom to be what? The smallest value possible. Well, for the bottom to be the smallest value possible, we know the resistor cannot be negative. Resistor is always plus. So this value will never be negative, so they can't cancel each other out. But the imaginary portion, if you have an inductor, for example, 5J, and you put a capacitor of negative 5J with it, what's going to happen to that number there? That will go to 0. So R sub L here, the only way to be the smallest number, so you really want to be the imaginary value here to cancel each other out. You want XL to be the opposite to X Thevenin, because you want the bottom to be 0. I could have done the math a little bit better without going through this, actually. I don't like the direction I took the math in. And since R sub L, you can't change it, so in this case, you're saying, well, I want ZL to be R sub L, and now instead of being plus X Thevenin, I want it to be what? Minus X Thevenin. Because when this is equal to the opposite of that, this piece will disappear, and you get the smallest value on the bottom. And that'll give you the maximum power transfer. Again, the other way, take the derivative and set it equal to 0. That'll be more work. So when you look at Z Thevenin here, we had Z Thevenin to be what? R sub L plus J X Thevenin. This one's going to be J here. This one's going to be minus of that, so that number is really the conjugate of that. So for maximum power transfer, the other video we did actually with maximum power with a derivative, probably better than this one, the derivation. You want Z Thevenin or Z load to equal Z Thevenin conjugate. That's where you want the load to be. The conjugate. So if, what does that mean? If Z Thevenin is equal to 4 plus 5J, for maximum power, you want ZL to equal what? 4 minus 5J. The other way, actually, of looking at it, why you have the maximum power, I thought of it just now, you know, this idea. What did we say, for example, the average power? Let's go to average power. P average. What was it? 1/2 V max, I max, cosine what? Theta V minus theta I, right? What is the largest value this can have? This one. What is the largest possible value this can have? The cosine. Any cosine function. What's the biggest value cosine can have? Cosine theta. Cosine is 1. That's the biggest number the cosine can be. So if you want that number to be the largest number possible, you want that to be 1. Well, for that to be 1, what do you want the angle? Cosine of what angle will give me a 1?
180.
Try again. That's negative 1.
90.
90 is 0.
Oh.
0. You want theta v minus theta I to be actually difference 0 degrees. There is no difference in the phase shift. Well, what happens when one is the conjugate of the other? What happens when you have, let's take this source, for example, of 5 angle 20. And you put in now here, no, let's put in just a value here of 6 plus J10. We're saying you want the load to be what? 6 minus J10. The conjugate, right? So what happens when you add these two numbers? You will have 12. What is your current going to be? 5 angle 20 over what? 12, which is 5 over 12. What's the angle? Angle 20. Notice the difference between theta v and theta I. What's the difference between them? 0 degree, which makes the cosine equal to 1, and you will have a maximum power transfer. You will notice the voltage and the current are in phase. If you're in the lab and you're playing with that, you'll see as you're adjusting this value, you'll see one is peaking before, one is after, but as you adjust the value, they start to go close toward each other till one on top of the other. They peak at the same time. That's when you have a maximum power transfer. But the equation for maximum power transfer, if you were to circle that anywhere, is you always want to have that Z load is equal to Z Thevenin conjugate. That's what we use. That's what you have to. This just the rest is derivation for that.
What if any of the sources are out of phase? Would there be another way to?
What do you mean out of phase? Source itself could be any phase.
And then like if that one's like 30 and the other and like I is 20.
Then you wouldn't have maximum power transfer. There'll be some shift there. You'll have a power there. We calculate. Remember we calculated that with the instantaneous power and the average power.
Be a way to find maximum power transfer if they had different.
Yeah, you can, sure. What is it? Average power, 1/2 V max I max cosine theta V minus theta I.
Will that be average?
Yep, instantaneous. Once you know what they are. The question actually, in case you can't hear it here, the question, what happens if you have, for example, a voltage of, let's say 20 angle 30 degrees, right? And a current, it's not at 30 degrees, it's not in phase. And I said, it doesn't have to be. This is for maximum power. You want that to be the conjugate. It's not always the case. What happens if this was 6 plus 2J or 6 minus 2J? So the current will not be in phase with that. Let's say it was 2 angle 13 degrees. And let's assume W for us was 4,000. So if you want to find the average power, P average is going to be 1/2 V max, which is 20, I sub max, which is 2, cosine theta V minus theta I. That's the average power. If you want to find the instantaneous power, and that's what your question is, well, this one would be what? This is 20 cosine 4,000 T plus 30, but that's in radian and degrees. I mean, you got to convert to radian. So that's 30 times what? Pi over 180 to make it in radian. And this current will be what? 2 cosine 4,000, I said here, right? 4,000 T plus the 13 degrees, and I convert that to radian, pi over 180. So my average power as a function of time is going to be 20 cosine 4,000 T plus 30 pi over 180 times what? 1/2. Oh, I'm sorry, no, it's 1/2. Times 2 here. I'm looking at the wrong spot. Times 2 cosine 4,000 T plus 13 pi over 180. And the question, can I figure out what the maximum power? Sure you can. Let's do the math. That's 40. Cosine. Instead of writing that number, let's find what that value is. 30 pi, that's pi over 6, is it? What's pi over 6? Pi divided by 6, 0.524. Cosine 4000 t plus 13 pi divided by 180. That number is 0.2268. Now you're going to use your trig identity. Cosine, cosine. Cosine, cosine. Cosine alpha, cosine beta is equal to, what is it? 1/2 cosine alpha plus beta. It's not on the board. I'm just working it backward. Plus cosine alpha minus beta. That's what a cosine. So I can write that as 40 times cosine. Let's add them. Add this to that. 4,000, that's 8,000 t. Plus, let's add these two numbers. That's almost a 7. 0.524 plus 0.227. 0.751 plus cosine alpha minus beta. This is alpha, that's beta. Subtract them. 4,000 minus 4,000 is gone. 0.524 minus that number. 0.297. Right? Now you want maximum power transfer, right? To get maximum power transfer, you take any maximum value, you take the derivative, set it equal to 0. Derivative and set it equal to 0. There's my derivative. What is the derivative? Cosine. Negative sign, isn't it? I'm leaving a space here. Sine 8,000 t plus 0.75 times the derivative of this, which is what? 8,000? Plus, what's the derivative of any constant? Isn't that a 0? That's a number there. Cosine 0.297 is like a number, 0.3, 0.2. The derivative of that is 0. Set that equal to 0. That's the derivative. So now 8,000, because you can divide, actually you can even drop all the numbers in the front if you divide both sides. For this to be 0, that means the sign has to be 0. I can drop the other numbers. I'll leave it there for now because I know some people are going to say, how'd you come up with this? So what is negative? What's 4,000? That's 0, 0, 0. 0, 4 times 8, 32, right? Let's divide both sides by, that's why I decided to leave it there, so you don't get confused. I was about to jump to this step in one line and just go the sine and we can tell you when actually that function will have a maximum power, at what time. And once you know that, you know what the current, you know what the voltage. Why? For the sine to be 0, well, we know this has to be either 0 degree or 180. Sine of 0. So one of them is 8,000t plus 0.75 has to equal to 0, or 8,000t plus 0.75 has to equal to pi. This can't be the top one. Why? Because t will be a negative number. when you solve for t. And that's impossible. The time can't be negative. So you take this and set it equal, okay? Move that 0.75 there. Pi minus 0.75. .392. What is t equal to? Divided by 8,000. It is 0.3 millisecond. 0.2989, so 0.3 millisecond. At 0.3 millisecond, you will have a maximum power sent to that load in that case.
So it depends on the time in that
Correct.
case? But for if they had the same phase, it wouldn't matter for time?
Yeah, because the sine cosine, if where's the math stuff here? If you're looking for phase or no phase, what will happen actually there, that current will have the same voltage as this. You know, these numbers will be the same. So if the numbers are the same, they have the same value, this will be squared. Still, if you want to find the instantaneous power, it has to be at time. What time?
For instantaneous power?
Yep. That's what you're asking me, for instantaneous power. It doesn't matter if it's in phase or not in phase, because if it's in phase, these two will be the same. So I don't have to use a trig identity. I can just square that, take the square root of it.
But for maximum power transfer, do we really need to consider the time?
No, because you asked me for it. That's why I answered this one. You asked me what's the maximum power transfer, so you don't want the average.
So
I had to derive that for you.
So if they're in phase, it's non-time dependent, but if they're out of phase, it's time dependent?
No, there will be both. For instantaneous power, both will be time dependent. Yep. Because you still have to take this and square it. It's still going to be a function of time. Because that equation here, your current and your voltage will be the same in terms of phase. The angle the same. So if the angle is the same, this cosine will be the same. So you still have the cosine there, except these numbers will match. That's the only difference. These numbers will match, so I don't have to use the trig identity. That becomes a square, take a square. It's still a function of time. So if you look here in our book, and it says for maximum power transfer, we did the average power last time, and the average power is 1/2 V max isomax cosine theta V minus theta I. We're talking about maximum power transfer will be, actually, for that to happen, you want that to be the average power, the maximum average power. So if you want the maximum average power, that doesn't care about the time. It's actually going to be 1/2 V max isomax, as this will be a 1.
Okay.
So now, for maximum, it says, if you want to, for maximum average power to the load impedance ZL, we need to make sure that ZL equals the conjugate of Z Thevenin, or Z Thevenin conjugate. And there's the math going through it and deriving the math through it.
The conjugate is always just the opposite of...
The imaginary portion is always the opposite. Yep. The real portion stays the same. The imaginary portion gets flipped around. So let's take an example here, Nick. We'll put some numbers in it. If I have this problem, this would be a quick one, doesn't take that long. It's an AC source, obviously, with the value of 3 angle negative 3 degrees. That's voltage here. Going through a resistor of 500 ohms and an inductor of J3, if I'm seeing that correctly. And now we have a load here, ZL. And the question now, what do you think find ZL for maximum power transfer, average power transfer?
Just 500 volts,
Maximum average power, that's what we're looking for. Maximum average power. So I need ZL to equal to what? 500 minus 3J. Now, if you want to calculate, what is that average power, by the way? If you want to calculate what the average power is, we can figure that out. So the current now, I through the load, will be what? 3 angle negative 3, 0, divided by what? Divided by 500 plus 500 here. Remember, this is going to be 500 minus 3J. So when you add this 500 to that 500, what are you going to have? 1,000, which is 0.3 angle negative 3 degrees. What is the voltage across the load? That's voltage division. 3 angle negative 3 times what?
1,000.
Well, 500 voltage division minus 3J over the sum of them, which is what? 1,000. Or you could have done it by taking the current times that value. Do I really need to calculate that? Probably not. Why? Because if you remember, we can calculate that and find what VL and go, okay, we know it's 1/2 V max I sub max cosine theta V minus theta I. So let's see what that number is. Times 500 comma minus 3 divided by 1,000. I came up with 1.500. That's what I got here, which is obviously that's half the number. Yep. Angle what? Negative 3. Yes.
The current is 0.003.
Yeah.
Point milli. That's what I meant to say. You know, that's my intention, was over 1,000 is a milli.
Okay.
Yep. But you're right, it's 0.003. Should be 3 milli, I think. 3 milli, not 0.3. 3 milli. So now, what is the average power? It's V max, or 1/2, V max, I max, cosine, theta V minus theta I. 1/2. The V max is what? 1.5. I sub max 3 milli. Cosine of 0, which is 1. Point 0.003 times 1.5 divided by 2. It is 2.25 milliwatts. When I started doing this, I thought about it like, what am I doing it this way? Why am I calculating this? Because a different idea hit me once I know what the current through it. So this is method 2 now. Once I know what the current through it, if you look at the load, this is what your load looks like. You have a resistor of 500, and you have an inductor, which means a capacitor of negative 3J. Right? That's the load. That's your ZL. And if you recall, we said last time, if you only have purely inductive load, like you have a capacitor or inductor, the average power is what? 0. So the power absorbed by the capacitor, the average power is 0. What about the average power by the resistor? The average power by the resistor is what? Last time we derived that. Oh, not PT, the average power, not instantaneous. It's 1/2. You can use I squared times R. And I for that, what's the current through it? The maximum value, 0.003, right? You square it times R, and what was R? 500. And you divide that by 2. Does that give me the same answer? Does that give me 2.25 milliwatts? That's why I started thinking after I did the problem, like I should have done it that way. 0.003 squared times 500 divided by 2, and well, you know, 0.002225. So it is 2.25 milliwatts. I could have done it that way. Instead of finding the current through it, find this, and I mean, it's not much work really there. But notice both answers give me the same thing. Now, if you recall, while we're talking about this average power, and I'll try to wrap it up, because the book now brings in the effective value, the RMS value, which we talked about that before. For a sine function or a cosine function, we found out that the effective value, the effective or RMS, we call that RMS, the same thing, root mean square, is what? The maximum value. What was it? Divided by the square root of 2. Remember that? I effective equals, or IRMS, which is I maximum for a sine cosine divided by the square root of 2. If it's not a sine or cosine, look at the previous videos. We did that and we found out different answers. It's not always the square root of 2. Depends what shape we have. We done that maybe 2 videos ago. So if you do the math here, you will notice that Vmax equals the square root of 2 times Vrms. And you'll find out that I sub max mathematically here is the square root of 2 times IRMS. So back to the average power. What was your average power? It's 1/2 Vmax, I sub max, cosine theta V minus theta I. Let's replace Vmax with the value of it, which is what? Square root of 2 Vrms. And let me replace I sub max by the square root of 2 IRMS. And what's going to happen to the square root of 2 and the square root of 2 when you multiply them? That's a 2, that will cancel that 2 in the bottom. So you end up with the average power equals Vrms times IRMS cosine theta V minus theta I. So when you're doing these problems, look and see, is the value given to you RMS or is it given to you as a maximum value? If it's RMS, you have to use this equation. If it's maximum value, you gotta use the other equation.